Okay, hello to everyone to our today's 10th and also 11th presentation in the frame of our online seminar on interval methods in control. And it's our pleasure to have two speakers today who will join together in our time slot. The first speaker will be Bernd Tibken. He's a full professor at the University of Wuppertal in the area of automatic control. And yes, I've been working together with Bernd, I think, since 20 years or something like that,
nearly,
in various projects concerning modeling, control techniques, and also interval methods for sure. And it's really my great pleasure to hand over the microphone now to Bernd, and he'll talk about some fundamentals on the observability analysis of nonlinear systems, including injectivity. And this will be the introduction more or less to the second presentation today, which will focus more or less on the interval method side. Okay, Bernd, the floor is yours.
Yeah, Andreas, thank you very much for the nice introduction. You already gave the title of my talk, and my talk is organized in the following parts. After an introduction, I will state the problem, then introduce Lie series, which is a very simple tool at this part. For more complicated systems, we would use Lie series, and then we reformulate a little bit, and then we show which injectivity condition we use in order to prove or to check observability of such a nonlinear system. And first of all, our system is given by this state space representation. The differential equations. F is usually a nonlinear function of the state vector. We have no inputs at this in this very simple presentation. If we have inputs, then, as I already said, we use, instead of the Lie series, the Flie series to check observability, and then we have to be a little bit more careful in the definition of observability. This is the initial condition, and Y is the measurements which can be made on the system. And the measurement equation is usually also a nonlinear function of the state vector, giving the connection between the state vector and the output vector. In very simple terms, each component of H corresponds to one sensor in our system. And usually you have much less sensors than states. For example, at the International Space Station, the number of states of this X is several 10,000, and the number of sensors are several hundreds. And so the dimension of Y is usually much lower than the dimension of X. And now we would like to define what is observability. And in order to do that, we introduce two different initial conditions, Z1 and Z2. And Z1 corresponds to the output Y1, and Z2 corresponds to the output Y2. And observability can now state it very simple. If for all Z1 not equal to Z2, we have Y1 not equal Y2, that means the outputs are different. If the initial conditions are different, then our system is observable. This condition has been stated already by Hermann and Kräner at the beginning of the 70s for nonlinear systems, and for linear systems, it has already done by, I think, Kalman and Busey in 59 or 1960 in their seminal papers on the Kalman-Busey filter. And this is the thing we are after. And what are the problems with this definition of observability? First of all, we have to check all different pairs, Z1 and Z2, and then we have to check the output of such a nonlinear system for equality, two outputs for equality. And as you all know, even when you simulate this here, you have simulation errors. That means it's not, in general, not possible to compute Y exactly. So this comparison is on the time basis very, very difficult. And therefore, we need some extra thoughts to obtain a obtain a checkable condition. to check observability. For linear systems, this will all end up with the Kalman observability matrix and a simple rank conditions. For nonlinear systems, it's a little bit more complicated. And I already gave it here already, statement of the problem, how to check this observability, find a computational condition, and simpler problem, don't check it in the whole state space, but check it for initial conditions in an interval vector. I denote this by x capital power to capital Y I. And this is a kind of local condition, namely only check pairs in this vector, in this interval vector. So what can we do about this? First of all, like in the linear case, we have a series expansion for the output, the Taylor series expansion, and this is called here Lie series, named after Sophus Lie, approximately 140 years ago. He stated this connection. This is simply a Taylor series with respect to the time, and the coefficients are these Lie derivatives. And the definition is given here. So the first Lie derivative is simply the Jacobian of h times f. The zeros Lie derivative is h of x, and Lie derivatives to the power L plus 1 is Lie derivative to the power of L, derived again along this vector field f. And if f and h are real analytic, y of t is a real analytic function. So this expansion is possible. If you want to see more, read more about this, the best source is maybe the book of Isidori on nonlinear control systems, where this Lie series is introduced, and also the Fleece series is introduced, which is available when you have inputs. What's the problem with this? If you compute this for linear systems, it's simply nothing else than the matrix exponential function multiplied by C when you have a linear system. And you can sum it up. In the general case of nonlinear systems, first of all, you have no general equation for this kth Lie derivative. Then even in the polynomial case, if h and f and h are polynomials, these functions here grow more than exponentially in complexity. And there's no real chance to sum up this series in contrast to the linear case. So what can we do about this? Yeah, we simply check. We simply state, okay, yi is this Lie series where we have introduced for the initial condition zi, and now we check not y1 not equal y2, but we check the bad boys. We check this condition which states that the outputs are equal, and that means the corresponding initial conditions cannot be distinguished. And this leads at the end to a checkable condition. If we set this here into this equation, we have this equation, and now we can make a comparison of equal powers in this power series, and we can replace this condition, which is given by in continuous time, and which is a denominable number of conditions. We can replace this by this number of conditions, which is numerable. We can index them from k to 0, 1, 2, and so on. Here's a small typo. K has to start at 0. Excuse me for that. And we have thus this condition is replaced by this set of an infinite number of nonlinear equations. And we have to check that these conditions give Z1 equal to Z2. So that only in this case, this can happen. And that means the observability is fulfilled. And in order to save a little bit of notation, we simply define the observability mapping, capital F of X, which are simply the components of these equations here. Given here, we state it as X, and then we have simply an infinite number of equations, of components here. And if f of Z1 equal f of Z2, and if from this equation it follows uniquely Z1 equals Z2, then the system is observable. Now we have replaced everything to an infinite number of equations, we can give that also afterwards. In one of my publications, already dating back to 2004, for polynomial systems, I showed how this can be really checked via computer algebra systems. And if we look at this condition a little bit more closely, then this is simply injectivity of F. So if we have the same image, then the origin has to be the same already. And first of all, it's also clear if this holds when we only select a finite number of the components of F, then it already holds for the whole set of the equations. So sometimes a finite number of components is enough to get this conclusion, and then we have observability. And therefore we go in the first step to a finite number of columns. And now this is a little bit full. We have this equation. We go into this interval setting here, interval vector setting, and we want Z1 equals Z2 uniquely. This is, here's a small typo. This has to be a minus sign. F of C, we bring this part on the other side. The idea is to, if we have F of Z1 minus F of Z2, to apply some kind of mean value theorem to extract some more information out of this equation. So first do it in a scalar case. If we have a scalar function g and we have two different arguments, then it's well known that the difference of these two values can be written as a gradient of this function g at some intermediate value multiplied by Z1 minus Z2. So, and if this is not equal to 0, then from this equation it immediately follows if this is equal 0, then also Z1 minus Z2 is equal 0. And this is the scalar case. Now in the vector case, if G has more components, so G is a subset of the components of F, then this difference for the ith component is, here's also a small typo, this is Z1 minus Z2, and here we have GI at an intermediate value somewhere between Z1 and Z2, but for the different component functions G, this intermediate value is different. And this is given here on this part of the slide. In this vector case, we have here the first component, the gradient, namely at this intermediate point up to this intermediate point, here multiplied by Z1 minus Z2. And this is a matrix. And the problem is this matrix does not correspond to the Jacobian matrix of the function g at an intermediate point, because we have here these different intermediate points. Here's a connection to the well-known Jacobian problem, where the question is, if the Jacobian matrix for all values has full rank, is the function injective? And in some special cases, this is true. But in a general case, you can see it here, this cannot be true because these intermediate values are different. And what can we do now? We know that if Z1 and Z2 are in this interval vector, we know also these intermediate values are lying in this interval vector because they are between Z1 and Z2 on this straight line between these two vectors. And that means this matrix M, we call it M here, is not equal to the Jacobian matrix at some intermediate point, but it is included in the interval extension of the Jacobian matrix with this interval vector xi, where all these vectors belong to. And that means if M has full rank, then Z1 minus Z2 is equal to 0, because if this matrix has full rank and we can set this to 0 here, then this has to be 0. And that means G is injective. And how do we check this? Yeah, the problem is we don't know this matrix. We only know it's contained in this interval matrix. So the trick is check the interval matrix for full rank and then get this corresponding result here. And if this interval matrix has full rank, capital F is injective and the system is observable on this interval vector xe. Here's also a small typo. This e has to be in the above the x. So how to check MI full rank? So we apply, and this will be done by explained in the talk by Thomas. We apply a result of Criterion in order to check an interval matrix for full rank. This can be, there are several results available. The first going back to Hermann Weyl, which can be used for this purpose to estimate eigenvalues and singular values. But in general, it's NP hard. That has also been proven by Giri. It's in general NP hard to check an interval matrix for full rank. But there are some sufficient conditions available, which are quite strong. And they are used by Thomas in order to check then observability on such an interval vector. And then pave the whole area in which we are interested by interval vectors and then checking observability. And this application will be given in the talk by Thomas. And now I'm at the end of my very short presentation. Thank you very much for your attention. And it's up to you. I can either answer now questions or we do it at the end together.
Okay, many thanks, Bernd, for your very inspiring presentation. And I think maybe if there are questions now, we can start immediately asking questions. And at any time, it will also be possible to do that at the end. Okay, is there anyone who wants to start with a question? Okay, if this doesn't seem to be the case, yes, Jürgen Garloff has a comment. Yeah. Jürgen, do you want to ask?
Okay. Yeah.
Ja, hallo, Herr Garloff. Ich kann Sie leider nicht hören.
Okay, sorry. Can you hear me?
Yep, now it's working.
Okay.
Yes. Yeah.
I would like to draw your attention to a joint paper with Stanislav Bialas, which we have published 1984 in the journal Linear Algebra and Applications, in this paper we have given a criterion for the injectivity of a differentiable function in Rn over a box. This criterion is as follows. Assume that we have found an enclosure for the Jacobian of the function over the box. Then by a famous theorem by Gehl and Nikaido, the function is injective if all matrices in the enclosure are P matrices. That means that all these matrices have all their principal minors positive. In this paper, we have shown that the P matrix property, the P property matrix can be inferred from a special set of vertex matrices of the enclosure. The cardinality of the set of vertex matrices is 2 to the n-1. So in the two-dimensional case, we have only to check 2 vertex matrices, whether they are P matrices. And that means that we have only to check 2 2x2 determinants for positivity. There are other similar criterions in the two-dimensional case. This is only a sufficient condition, but the condition by Tibken was also only sufficient. Should I give further explanations on this? So you have only to find an enclosure for the Jacobian of the matrix of the function over the box, and to have to check whether whether some vertex matrices of the enclosure have all their principal minus positive.
Yeah. How far is your sufficient condition away from the necessary condition?
I think this is not known.
Yeah, because the condition by Rohn is from 2017. I can distribute the corresponding bibliographical data on that, and I will have a look at your paper.
Sorry, the condition on the interval matrix is necessary and sufficient.
Your condition?
Yes, for the interval matrix.
Yeah.
We have the condition that we have to check only a finite set of vertex matrices is necessary and sufficient that all matrices in the enclosure are P matrices.
Yeah, and the P matrix condition, is that, how sharp is that? As you stated, when
what you are meaning by sharp?
Excuse me?
What you are meaning by sharp?
So if you have a generic injective function,
yes.
will this P matrix condition be fulfilled?
No. It's sufficient. Yeah. In the one-point case, the theorem tells if the function fulfills the P matrix condition, then it is injective over the box. Yeah, in this way.
Yeah. Okay. So we have to compare that with this Rohn theorem, for example. So the theorems published by Rohn go mainly the following way. They take this interval matrix, MI here, and then take the center of the matrix and the radius in some sense.
Exactly. Yeah.
And then they use the center to compute some auxiliary matrix, and when the radius is getting smaller and smaller, then at some place this condition then is fulfilled. So it's they rely on the fact that the intervals in this interval matrix shrink or have to be not too large in some sense.
Yeah. Okay.
And in the paper they gave examples where not too large is really quite large. So I can't remember exactly, but the width of the intervals is 10, 20, sometimes 100, and they can show full rank condition. But I will distribute that to all of you, and I will look for your paper, Professor Garloff.
I think the problem is that the theorem of Gale in the Keido we are using is only sufficient.
Yeah,
it's only a sufficient condition for the injectivity.
Yeah, we made a very intensive literature search for injectivity conditions, and you find nearly nothing. I know Gale and Nikido, and there are also some old papers by Hadamar, for example, on bijectivity and injectivity, and it's not very much around in the literature with respect to really conditions. The conditions we all know from analysis are if the Jacobian matrix has full rank at one point, then in the vicinity of this point the function is injective. But nobody tells you how large this vicinity is, for example. And we need a really constructive and computational criterion here. But thank you very much for the.
I think a good reference is a book by Paradowski.
Yeah, I know. In this Red Springer series. Huh?
Yeah, exactly. Yeah,
I know that book. Yeah.
Okay. So you are aware of it.
Yeah. Okay. No, this is. So thank you very much. I will look for your paper.
Okay.
Okay. Now we have a further question. Shaima has raised her hand. Shaima, please go ahead.
Hello.
Yep.
Hello, Andrea. Can you hear me?
Yep, that's working perfectly.
Okay, so thank you for this presentation. I think it is a very interesting presentation which deals with nonlinear systems. I have a small question. my question is about when the system is subject to unknown inputs, even internal or external, how complex will be the study of to study the observability or injectivity conditions when the system is subject to external or internal inputs?
Yeah, then we have to, thank you very much for this question. Then we have to replace this Lie series by the Fleece series. And if you have inputs, I've not prepared a paper for that. If you have inputs in the right-hand side here, in this F, can you see this, the equation?
Yes.
Yeah, then usually in the book, for example, by Isidori, and they wrote here a sum of G sub I times U sub I. So the inputs enter the right-hand sides linearly, multiplied by some vector fields they call G1 to GM or something like that. And what you then have to do is you have to use the Fleece series, which gives you this Y. And that's a series of non-commutable variables. And the coefficient of interest are the coefficients. And the coefficients are not the kth Lie derivative of H with respect to F, but you have all mixed Lie derivatives here. So you have Lie derivatives with respect to F, to G1, G2, and so on, and GM in all orders in a certain sum. And the condition here from here to here is then the same. So the Lie derivatives of all these functions G, which are entering here, have also be the same, like in this here. And this observability mapping is a little bit different and more complex because you have to get rid of the complexity of including all the G's here. But in principle, it's the same. You have to check the rank also, and then you have what is called more or less weak observability, which means for almost all inputs, your system is observable.
And we should know also the initial conditions of the unknown inputs?
No, we don't know the inputs. Like here, when we do this step from here to here, we use a result of from analytic functions that you can compare equal powers of t. And if you have here this non-commutative power series, then you use a similar theorem derived by Fleece, and which gives also the equality of the coefficients. So at that step, the influence on the U is disappears. Okay. So you cannot check, for example, bad inputs, which is also in nonlinear systems sometimes of an issue, to check if inputs can render your system non-observable, for example. And this is with this approach not possible. In that case, you have to use a different approach, which is, I have no good literature now in mind, but I can look for it and send it to you. Then you can, for example, check what conditions your inputs have to fulfill in order that your system is observable, for example.
Okay, thank you for you.
Okay, many thanks for the discussion. Are there any further questions?